This is the third lecture in 7F. It is on Simpsons Rule for numerical integration for Calculus 2. In the rules we talked about before, the right, left, midpoint, and trapezoid rule, we were approximating the function in each mesh by a linear function, by a line, either a straight line for the midpoint left and the right-hand rule, or a diagonal line for the trapezoid rule. Okay? For Simpsons Rule, we don't use a line anymore. This is a nonlinear approximation. It's a quadratic fit to the curve. And here we're going to use a parabola. So the general expression for the parabola is a x squared plus bx plus c. Okay, so we have three coefficients that we have to determine, and we determine it by using 3 points of the curve. In other words, we make this parabola, which is p of x, our approximated parabola, fit the curve in 3 places. If we remember from those other cases, we made our rectangle fit the curve at 1 point, either the left, the right, or the midpoint. Here we make the parabola fit the function at 3 points. If these are two adjacent meshes, which is what, it's not really the midpoint. Say this is x0, and this is x1, and this is x2. When you borrow other people's graphs, sometimes their notation doesn't agree with yours. Okay, so here I'm going to make the parabola fit the function along these fence posts of the mesh. So I need 3 points I need to fit. And I'll say the parabola has to go through these points. It won't necessarily fit the function off of those 3 points, but we're assuming it's not going to be too bad, especially if our mesh is small enough. In order to fit the mesh and have it match those 3 points, we end up needing to have an even number of meshes and an odd number of x values. And I have written this wrong. I see. This is 10. I couldn't count. So I'm starting with x0 and I end up with x10. And that's my 11 values of x that mark off these 10 meshes. So the number of endpoints has to be odd. The number of subdivisions, that means your big N, has to be an even number for Simpsons Rule. For Simpsons Rule, we end up with a form that has a lot of similarity to that trapezoidal rule that we did before. It's a little more complicated to get there. I'm going to hit the highlights. You can then go and look again at the derivation in the book to really understand it. So here's what we have. We have those three, the parabola, and we have the 3 coefficients in the parabola, a, b, c, and we need to find values for them. We're going to start off by saying that our function is meshed with a mesh size of h, but that it's going right over the origin. That's going to make things a little bit easy to derive this. Okay, so here's one mesh right here. Here's the second mesh right next to it. It looks like that. So this isn't the endpoint x0. Here's the point x1, and here is x2. Okay. And now I want to make, say my function looks like this. I somehow want to make the mesh fit these 3 points. Might be a little hard, but okay. So I want to equate my parabola, my ABC parabola, to the values of the functions at this point. Right here, f at x minus h1, I'm going to call that y0 just so that I can not have so many things to write. Right. Here, I want the value of the function at 0, which I'm going to call y1. Doesn't seem like you should make the 1 and the 0 go together, but remember this is point x1. And at the endpoint here in this is the value of the function at h, and I'm going to call that y2. So by making this association between the parabola and the value of the function at these endpoints, I end up with 3 simultaneous equations for a, b, c. The first one, x is minus 1, so I put minus 1 in here for the, or minus h, I put minus h in here for the x's, and that has to equal to y0, which is the value of the function there. At x1, x is 0, so you see the zeros are here, and that has to equal y1. At x2, x is equal to h, so I put the h's in here, and that has to equal to y2. So we have to solve these three simultaneous equations, but we get a good head start here, because you notice in this case, we end up on the second line with y equal to y1, or c equal to y1. Alright, so now I've rewritten our simultaneous equations, making use of the result we saw for the second line. Look at the next two lines. One contains minus bh, the other contains plus bh. If I add them together, I get an expression for a. So I have an expression for y in terms of the function. Now I have an expression for a, 2ah squared, which actually is fairly convenient. We'll see that in a minute. And it's in terms of y0, y2, and y1. It's a little more complicated than c1, but that's okay. Now we have to find a value for b, or do we? We don't. We don't really care about this parabola at all. We only care about the area under the curve. When we take that area under the curve, b drops out. So here we are integrating that parabola from minus h to h. There's actually an x here that got forgotten. Okay, so now after we integrate, notice that x is odd here. It's odd here with the power of 1, but it's even here. So when I evaluate it between minus h and h, this term drops out. And all we need is 2ah squared plus 6c. Well, if you know from before, we knew what 2ah squared was already. We can multiply y1 by 6. And here we have the integral under that parabola only in terms of the function values. And that's what we want. We don't really care about the parabola. Remember, we only care about in terms of the function values. This is your answer for integrating, for approximating the function by parabola, and then integrating under that parabola. So now that we did mesh 1 and 2, let's go and do mesh 2 and 3. 1 and 2, now we have to do 3 and 4. Remember, mesh 3 and 4, well, that's the first mesh. So here's going to be mesh 3 and mesh 4. Mesh 3 is flanked by x2, so the value of the function here we'll call y2, x3, and then here we go up here to x4 because of the scheme that we developed 2 lectures ago. Alright, and here's the answer. We don't have to worry about any approximating rectangle. We're not multiplying height times width. We're integrating under that parabola. Alright, and the mesh is in here, it's h, but it's h over 3, and you have y2 plus 4 times y3 plus y4. So now let's go from mesh 1. So we're going to add up the results for 1 and 2 and 3 and 4. And here's what we get. I wrote them in a list here. Now I'm going to factor the h over 3 out and put everything together. And now I have the start of the result for Simpsons Rule. Remember the trapezoid rule? The value of the function at the endpoint at f at a was by itself, and that's this one right here. Here's the value of the function at the other extreme point. And the intermediate ones for trapezoid rule were all multiplied by 2. For Simpsons Rule, they're multiplied by 4 and 2 and 4 and 2. See this pattern? And this pattern will persist. So here is the general pattern for Simpsons Rule, written out. So we're integrating from a to b of f of x dx. It's multiplied by step size over 3. And now between, at the edges, we see the value of the function at a, the value of the function at b occurring by themselves. And on the interior points, the pattern goes 4, 2, 4, 2, 4, 2, 4. Right? So it's a little more complicated, but the results are so much better.